Okay, we're going to break into some new territory today. And sorry I'm not there in person. We're trying to deal with sickness. You're going to get some interludes here with the kids in the background heading to school. And I got Ethan here with me, who's feeling better, but still kind of sick, huh, buddy?
His hand is this tall.
Do you want to say hi to my class? You want to say hi? You want to talk to him? Say hi. Come say hi.
Hi.
Yeah. Okay, he's here with me. So anyway, partial fraction decomposition.
Hi.
Hi, yep, they hear you. So there's a part to this. It doesn't see decomposition up there, but you remember that in pre-calc, that stuff. Logistic growth, that's probably pre-calc for you guys as well. Two topics that come back, and they end up being unique topics for Calc 2, the BC exam. And so we want to address kind of what it looks like for the exam, and then, of course, conceptually, what on earth is this stuff? It's really applicable, good stuff. Very interesting. So things that grow exponentially, they're things that the rate of their growth is proportional to the actual amount, the quantity of the growth. So the idea of that is when you have y equals e to the x, the derivative is e to the x, or y equals e to the 2x, it's 2e to the 2x, the derivative. So proportional to its growth rate, the actual amount that you have is a unique factor or the quality of exponential growth. Well, not everything can just grow indefinitely. There's limits to how that happens. There's a capacity, and that's where logistic kicks in. Yeah, capacity. So that's really important. So first off, let's talk decomposition, partial fraction decomposition. We'll reteach that here in a few minutes, but if you have two fractions, if you had to add them together, the only thing that works is two common denominators, and then you add the numerators. These two do not currently have the same denominator. So do you remember that process where you have, this is the end result, AD, the diagonal cross products? Have you ever learned that before? That kind of crisscross stuff, A times D plus the other diagonal product, B times C, all over BD. If you don't remember that, basically what it is you multiply each fraction by the other denominator. Yeah, you can have that, sure. And then so B and B gets multiplied on the right-hand side, that you multiply by the other denominator. And that looks like, if you notice, you're multiplying by the diagonal denominator to get this to work. So if that strikes a chord for you, great. If not, then let me know how I can help you. But that's the way to add fractions. Well, decomposition is going backward. What if we have a fraction with a common denominator and we want to bust it into two fractions with none-like denominators? And that there lies our work. Okay, so continuing on. Oh, got to help someone with his shirt. Okay, so let's see. We'll have a few more interruptions along the way, I promise. So the big deal on this logistic growth, let's talk about rumor, spreads at school. First off, you've got this rapid growth at first. Something gets out there that has to do with, I don't know, Mr. Silly and his extra toe. And then you guys start talking about it, mumble, 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 and a few people hear, and then it tweets out, and of course it takes off. Well, initially things take off really fast because there's a whole bunch of people who haven't heard. But eventually you get to a point where a threshold where most everybody's heard, and so that spread of the rumor slows down. There are fewer candidates, fewer hosts for this rumor. And so you see the students who haven't heard ratio to those who have kind of changes. It changes tides. And that changing tide moment, kind of in the middle there, you'd notice that as an inflection point, right? That point is exactly halfway between. So an inflection point, the turning of the tides where there's suddenly people who have not heard is getting smaller, and the students who have heard is growing, but the ratio of those two has changed tides, and so ready to roll. So now, logistically, growth carries until there's a carrying capacity, 2,000 students. I mean, for whatever we have in our school, we're almost at 2,000 students. You can only spread the rumor to as many students as there are in the school, and that's the limiting capacity. Okay, hang on. So there you are. That's the scenario. 2,000 students, the max we can hear. So in there, there's a curve that goes with it, and you've probably seen that back in pre-calc days. We'll reintroduce that. But the derivative, the differential equation that describes this kind of change, you have the carrying capacity L incorporated into this function right here. Well, L and the Y is the actual number of students who have heard the rumor. So this difference between the total number of students and those who have actually heard that rumor is proportional. So you have the idea of this proportionality being multiplied by some kind of k. There's a proportional relationship between those who have heard and yet to have heard, and that's the rate of change is proportional to those who have heard and those who have not heard that particular rumor. So Y would be heard. Sorry, I'm kind of doing three things at once. Can you tell? And this would be not heard. There you go, not heard. Ethan's got his pants on. little did you know that was taking place at that moment. Okay, so herd and not herd is what the L minus Y represents. Y represents herd, proportional to the product of those two, and that's the rate of change. Now, an interesting thing is that dy dx or dy dt formula looks great, and that's the one you want to know and memorize. They try and mess with you on the exam and ever so slightly change that up and make you figure out where the L and where in the K are in that particular expression, but we'll work on that as we go. Let's talk about the decomposition stuff. So down below, you got these two fractions. First, what we can do is, let's get a common denominator. Let's compose this one down below as opposed to decompose. So the idea is this little diagonal product here, that's how we start this thing out, x minus 3. And then the other diagonal product, that'll be your other part of the numerator, and use the sign that's in here, so the minus. So 5 times 2x minus 1, okay, all over the product of the two denominators. So there you have it. Oh, by the way, I'll put a little note at the beginning of this. I don't know if this is printed for you guys, and I hope you're just doing notes kind of freehand, if nothing else. So improvise as best you can. I don't know if these got printed off for you. And if they didn't, no big deal. This is still good information. Put it on some of that scratch paper I've got over by my little mirror and coffee maker if you want. Or make your own. Just bring your own paper. But that's it. That's composed. They put them together. Of course, we want to put things together that are like, distribute the 5. You got 5x minus 15, and then minus 10x, and don't forget plus 5 at the end. Just be real careful. The product of the denominators, usually we don't put them together. It's kind of nice to leave them separate. There's advantages to having those separate rather than foiling it out. Things like finding vertical asymptotes or holes and things like that. Looks like I got like terms and like terms. Yeah, so we're good to go. So I'm going to say my this thing put together, composed, would be negative 5x, negative 15 plus 5 minus 10, and then over. Let me know if something funny happens in there. Laugh at me if I'm making a mistake. You know, happens. That's it. That's the story on composing. So we're going to decompose, right? Next page, as I turn it over, and we'll roll with that. All right, so we'll take it to this example 2. You may have to write this on your own paper. So here's the deal. We're going to take that fraction and decompose it into two fractions added together. Because as it is right now, you might be thinking long division. Maybe we can simplify this here. You can't. We only do the long division when it's the numerator is greater than or equal to the denominator's degree. So numerator degree is equal to or greater than the denominator degree. Right now we have bottom heavier. It's the low heavy side process. We get the denominator bottom heavy causes some issues where we have to decompose it. So here goes. The process looks like this. First thing we want to do in a partial fraction decomposition is get a factored denominator. It helps considerably. So if you remember your quadratic factoring, these will be factorable. And this, per the AP exam, they're factorable. And things like, hey, there we are, 2, 1, negative 3, negative 1. Those factors, if I do 2 times negative 3, and I add back, that's negative 6, and then 1 times negative 1 is negative 1 more, and it adds to negative 7. Awesome. I paired the 2 and the negative 3, so those go on opposite ends of the parentheses. So if you've got your factor down, that's how it factors. If you don't remember, you want to come talk to me. I'll remind you. I'll get you back up to speed. Here goes. So that's the denominator factored. Those become the denominators. Remember, when we're decomposing, we're putting into two separate fractions. If you remember, BD, the denominator's product, becomes the separate denominators if you're going backwards and decomposing versus you combine them when you're composing or putting it together. So now we have to find the numerators, A and B. So this is the fun part. So I've got this equivalent expression. I got the decomposed fractions. Here's the original composed fraction. They're equal expressions. They're just different ways of writing it. And the way we'll solve it is we'll do that little cross product thing on the left. So we got the A times the x minus 3 denominator, B times the other denominator, 2x minus 1, equals x minus 13. And then over their denominators. So usually I'd put under here, the 2x minus 1 times x minus 3 on the denominator on the left, and then just carry over the denominator on the right. Well, actually, those don't make much difference. To find A and B, I only need to set it. I already got the denominators equal. If I'm trying to find the A and B that make this expression equal to x minus 13, the current denominator, I can just focus on the denominators, ignore the denominator entirely. So we're just going to look at setting the numerators equal after this cross product business. And this is the solving. You actually pick an x that makes a or b cancel. So I picked x equals 3 first. That makes a times 0, which cancels that a part, go away. And then what we have on the right is b, and then see in the parentheses there, 2 times 3 minus 1. And then where there's an x on the right-hand side, you also put the 3. So you get 3 minus 13. If we solve for b, we get b equals negative 2. This works in any one of these cases where the numerator, when we're doing decomposition with a linear numerator, you can just do the quick cross products here. Bam, bam. Set it equal to the numerator on the original function. Put in a value that actually makes one of the letters disappear, so put in 3, so it cancels out the a. Now guess what we're going to do? Put in something to cancel b. So we'll put in a half, and then then fill in the x's for the rest of the problem. So the b cancels, we're left with a times 1 half minus 3, and on the right, 1 half minus 13. Probably should put a little divider there, it's getting a little condensed. And what we find is negative 2.5a equals negative 12.5 on the right. If you divide it out, a is 5. There you go, we got b and a, negative 2 and 5 respectively. We'll put them back in, and there you go, we decompose this. We have a new representation of the same rational function, but this one's integrable. If you remember, these are classic log integrals, and these are ones we want to recognize. If you have something, a constant over a linear function like this, totally a log function. Here's how it works out. 5, of course, you factor out, but it's 2 natural log of absolute value 2x minus 1. So basically, we turn it into a 1 over u. It's a u substitution, where the denominator is u, if you want to do it the long way. But there's a quick way, too. There's a 5 that we carried over from the beginning, right? And the 2 is because we would take the derivative of that inner function, so we'd have to have that. I'm sorry, there's a 1/2 in there, isn't it? Whoops. Now that I'm looking at it, I wrote a little bit fast there. My ninja writing got the best of me. There. It's a 1/2 that goes inside there, log of 2x minus 2. And on the next one, 2x minus 1, and then plus the factor out the negative 2 you see here, voila, natural log of x minus 3. We're done. Totally doable. 9 times out of 10, these are, linear numerator. It factors beautifully, and then you get a sum of log expressions as your actual integral in the end. That's part 1 of these notes. Take a break, maybe try a couple examples from the worksheet that I hope made it your way. If not, why don't you guys get back to finishing up the worksheets you do have and take a look at the key to that crazy integral packet that you guys have. You can now look at the answers and shoot me some questions. That would be awesome. See you soon.